Okay, so we're going to derive the D3d character table. And just as a preface, this is a great problem for us to go over in class. It's really one that you need to be looking at the models or at least a 3D representation of a model online through the Otterbein University website. This is a point group with a lot more symmetry operations than the one that we did before, C2V. And so the first thing to do, right, is you have to find all the symmetry operations. And once you do that, you have to classify them into groups using your intuition or the mathematical proofs, but we can just use our intuition here. So it's always best to find an example molecule. So for D3d, staggered ethane, the conformation where it's staggered, the hydrogens are offset here from each other. You can see this hydrogen doesn't line up with that hydrogen. The other word you may remember from organic chemistry is called eclipse, where the two hydrogens are online. But so staggered, ethane is D3d point group, eclipsed is actually D3H. But anyway, so we're going to find all the symmetry operations. And so there's no way to really do this on a PowerPoint presentation or on a whiteboard. You just have to look at an example molecule and find them for yourself. But here they are, and hopefully now that I found them for you, you can figure this out. So, or you can see them. There's going to always be an identity. Right, there's going to be C3s. That's the principal rotation axis. We know that because there's a 3 in the point group name. And so there's going to be a C3. There's the principal rotation axis. You know, these hydrogens can all interconvert 120 degrees. And you can do C3 twice, right? You can do 240-degree rotation or 120-degree rotation counterclockwise. Those two, we can assume, and rightly so, that those are very similar. Those are going to be in the same class. So we'll put those as 2C3. Then we have perpendicular C2s. Why do we have perpendicular C2s? We're in a dihedral point group, a D point group. Those always have, by definition, perpendicular C2s. And a reminder is that for any D point group, i.e. D3d, for example, you will have as many perpendicular C2s as there are, as the number of in the point group as the principal rotation. So this is a principal rotation here is a C3. So that means you'll have 3 perpendicular C2s. In other words, a DND or a DNH point group will always have n number of perpendicular C2s. So there's 3 of them here. You can see them right here. And that's going to take, you know, this hydrogen, for example, and flip it 180 degrees to here. Or this hydrogen and flip it 180 degrees to here. That's how those C2s work. There's 3 of them. They're all in the same class. They're all very similar. They just have different orientations. You have inversion. Remember, inversion is x, y, z goes to minus x, minus y, minus z. So we can check that we have inversion. Take a look at this. Maybe let's do this hydrogen. It's on the top of the molecule, towards the left of the molecule, and in front. And doing the negatives of all those positions, that's going to take us to this hydrogen. So we go to the hydrogen, go to the same atom. So there is symmetry there. So we want top, front, left to back, right, bottom. So those are opposites. So that's good. That's inversion. And then we also have S6s. Those are our improper rotations. And those you can see. You're going to do a 60-degree rotation, right, a C6. So this hydrogen would be rotated in between these 2 hydrogens. But then it's going to do sigma H following that. And so this hydrogen is going to go here 60 degrees, and then it's going to flip down. So that's how symmetry works. Now there's 2 S6s in this class. And let me get to that in a second. Let's just finish off with the sigma Ds. The sigma Ds you can see here. And the important thing is, why are these sigma Ds and not sigma Vs? Well, remember, an easy way to know this there's a rigorous definition, which is that they bisect C2s, right? And so you can see that the position of these mirror planes would bisect the C2s. The easier way to know is that, hey, we have a D here. So these got to be Ds, okay? So those are the three mirror planes. We're almost done. The one with classifying the symmetry operations. The last thing we have to do here is figure out why there are two S6s. And so, you know, why the simplest way to get things in the same class is to do an S6 twice, or an S6 3 times, 4 times, 5 times, 6 times, etc. Just like we did here. Like, look here, we had a C3, we did C3 twice. That was a unique symmetry element. If we did C3 3 times, where would we be? That'd be a 360-degree rotation, right? 3 120s. That would be back to an E. So it's equivalent. And what about a C3 4 times? What would that be? That would be the same thing as a C3, right? Because we went around in a circle and we do one more C3. So that's a redundant terminology. It's not a unique symmetry element. So we don't need that. What about S6? So S6 by itself, okay, that's fine. That's unique. S6 twice. What would happen to S6 twice? Well, you go 60 degrees, you flip it down to this hydrogen, then you do another 60 degrees, and then you flip it back up to this hydrogen. What did you do there? All you did is went from this hydrogen to this hydrogen net. That's the same as a C3, right? That's 120 degrees rotation. So you can walk through these. A C6 3 times is the same as a perpendicular C2. How does that work? Well, you rotate once, 60 degrees, flip. Rotate again, 60 degrees, flip back up here. Rotate again, 60 degrees, flip back here. You went from this hydrogen to this hydrogen. That's the same as a perpendicular C2, taking the molecule and going like this, right? You can go through this, a C6 4 times. Basically, any even number, the flipping of the mirror planes, the sigma H's are going to cancel out. So that's not unique. C6 5 times turns out to be unique. That turns out you can walk through it, but if you go 5 times, you're going to go 1, down. That's 1. Then you're going to go 2, back up. Then you're going to go 3, back down. 4, back up. 5, right in between these two, back down. So you went from this hydrogen to this hydrogen. That's kind of like a counterclockwise S6. It is a counterclockwise S6, an X6 5. Okay, that's unique. S6 6 times is going to be an E. Basically, because you're doing 6 C6s, so you went 360 degrees, and then you did 6 flips. It's an even number of sigma H's, so you went back to the same. That's the same as identity. So you have two S6s because you have an S6 and an S6 5. So this is the first part of coming up with deriving the character table, right? We have to come up with all the symmetry operations and figure out if they're in the same class. In total, we have 1, 2, 3, 4, 5, 6 classes. And we have 1 plus 2 plus 3, that's 6, plus 7, 1 more 7, plus 2, 9, plus 3. We have 12 different symmetry operations. So the order of this point group is 12. That's very important information to know when we go to derive the character table, which now we're setting ourselves up to being able to do.